issues harmonic mitigation techniques అండి. ఓకే సార్.
ఓకే సార్. ఇది పీపీటీ కాదా సార్ ఇది?
పీపీటీనే సార్. పీపీటీని పీడిఎఫ్గా కన్వర్ట్ చేసుకుని మళ్ళీ ప్రాబ్లమ్స్ వస్తాయని అదిగో.
ఓకే ఓకే.
పీపీటీ కూడా ఉంది సార్, అది ఓపెన్ చేయమంటారా? ఇదే సరిపోతుంది కదా, బాగుంది కదా.
అంటే పీపీటీదే ఫుల్ స్క్రీన్ వస్తుంది సార్ అందుకని.
ఓకే కదా సార్.
ఓకే ఓకే.
పీపీటీ ఒకసారి ఓపెన్ అవ్వదని సార్ ఇలా పీడిఎఫ్ కన్వర్ట్ చేశాను.
ఓకే ఓకే. ఒకసారి పీపీటీ ఓపెన్ చేయండి సార్, చూస్తాము.
పీపీటీనా సార్? పీపీటీ ఇంకో వేరే ల్యాప్లో ఉంది సార్.
అవునా?
ఓకే, దాన్ని మళ్ళీ మెయిల్ చేసుకోవాలి ఈ ల్యాప్కి.
అంటే పీపీటీ అయితే ఫుల్ స్క్రీన్ వస్తుంది సార్, మీకు పక్కన ఏం కనిపించవు, కాంటెంట్ నీట్
ఓకే ఓకే,
కనిపిస్తుంది.
చూస్తా ఉన్నాను సార్. అది కూడా ఓపెన్ చేస్తాను సార్, వచ్చేస్తాను. నో ప్రాబ్లం.
డౌన్లోడ్ చేయండి సార్ దాన్ని.
డౌన్లోడ్ చేస్తున్నాను సార్. హలో.
హలో సార్.
సార్ కొంచెం ల్యాప్టాప్ స్ట్రక్ అయినట్టుంది సార్, ఒక్క నిమిషం సార్.
ఓకే.
ఈ పవర్ పాయింట్ ఓపెన్ అవ్వట్లేదు. ఎస్ సార్.
ఓకే. ఓపెన్ అయింది సార్. స్టార్ట్ చేస్తాం సార్.
అవుతాం సార్, 1 minute సార్. సార్ కనిపిస్తుందా సార్ స్క్రీన్?
కనిపిస్తుంది సార్.
ఓకే సార్.
ఫుల్
సో
స్క్రీన్
నా
స్లైడ్స్
స్లైడ్స్ కనిపిస్తున్నాయి సార్.
కనిపిస్తున్నాయి. స్లైడ్ షో పెట్టండి సార్ ఫుల్ స్క్రీన్.
ఓకే సార్. ఓకే సార్.
ఎస్. ఓకే. ఎస్ సార్. గుడ్ ఈవినింగ్ everybody. So this is S. Khaza Khizar, assistant professor from CSE department and CRM member. I welcome all the faculties and students, those who attended for this faculty lecture series. And today's resource person for this faculty lecture series is Sri Kumar Reddy sir, assistant professor from EEE department. So I request Kumar Reddy sir to start the session.
Okay sir, thank you sir. Good evening one and all. My name is Kumar Reddy Chipati. Recently I joined as assistant professor in EEE department. So as a part of KSRM lecture series, I would like to give a presentation on power quality issues. Under power quality issues, what are the various harmonic mitigation techniques are available. So I'm going to discuss briefly in this half an hour technical session or half an hour presentation. So briefly, I'm going to discuss the following contents. That is the various definitions on power quality, the major power quality issues, various nonlinear loads, harmonic effects, harmonic filter classification, my current research, what exactly I'm doing now, and my future research, what I'm going to do in future. Briefly, I'm going to discuss in this half an hour lecture series. So let me discuss the various power quality definitions which I collected from various sources and from various textbooks and a common point of view. So the power quality perception varies based on various type of consumers who is consuming electric power. For example, if you take a residential customer think that power quality is nothing but a continuous power supply without having any interruption. Similarly, when you take a farmer who is consuming electrical power for agriculture purpose, he may think the power quality in a different manner, that is getting uninterruptible power supply for a duration of at least 6 hours. So then only he can fulfill his agricultural needs. Similarly, if you take an industrial customer, according to his point of view, the power quality varies. According to his point of view, the equipment, whatever connected to his industry, should not get damaged by the power supply. So, so that is, according to his perception, that is the power quality. So, likewise, there are n number of power quality definitions are available. So, these are the standard definitions which I collected from various sources. So one definition is any problem manifested in voltage, current, or frequency deviations that results in failure or misoperation of customer equipment. Some power quality simply defined as the supply which enables the equipment to work properly. Uh, it is also defined as it is a concept of powering and grounding sensitive equipment in a manner that is suitable to the operation of that equipment. It may be defined like this also. Ability of an equipment or system to function satisfactorily in its electromagnetic environment without introducing intolerable electromagnetic disturbances to anything in that environment. So, some simple definitions are also available. Deviation of voltage and current from its ideal sinusoidal wave shape. It is also defined as is a set of electrical boundaries that allows a piece of equipment to function in its intended manner without significant life expectancy. So, power quality. So, if you go to, for example, in general, we can say if you go to purchase any item in the shop, we can find qualities. Similarly, the power supply also having variety of qualities. Power quality without interruption, power quality without any voltage sag, without having any voltage swell, without having any interruption, without having any harmonics, without having any transients. Likewise, the quality of power supply varies. Some customer need some quality of power supply. As I said already, if you take a domestic customer, according to his point of view, power quality is nothing but getting the uninterruptible power supply. Likewise, the quality of supply varies based upon the need of a customer. So in general, these are the various power quality issues which affect the quality of supply. Transients, long duration voltage variations, short duration voltage variations, harmonics, flicker, notches, voltage unbalance, and lowering the true power factor. As you know, transients usually occur due to the sudden switching on and the sudden switching off loads. Transients are two types: unidirectional transient and bidirectional transient. Unidirectional transient is mainly due to the natural lightning. Whenever natural lightning falls on the power system, it leads to unidirectional transient. Bidirectional transient is due to the switching operation within the power system. Unidirectional transient involves high frequencies as compared with bidirectional nature. Unidirectional transient, that is natural lightning, is very dangerous as compared with bidirectional transient. When it comes to long duration voltage variations, are again three types: over voltage, under voltage, and sustained interruption. Over voltage is nothing but if the voltage envelope, the duration of voltage envelope is more than 1 per unit for a duration of more than 1 minute, that is over voltage. Under voltage means the shortening of voltage amplitude for a duration of less than 1 minute, that is termed as under voltage. Sustained interruption means that if the voltage or current is zero, the amplitude is zero for a duration more than 1 minute, that termed as sustained interruption. All these long duration voltage variations are due to the equipment failure or intentional outage. Then, then short duration voltage variations are three types: voltage sag, swell, and interruption. These variations are always occur which is less than 1 minute, for a duration of less than 1 minute. Sag is nothing but improvement of voltage profile which is more than 1 per unit for a duration of less than 1 minute. Swell is nothing but decrement of voltage which is less than 1 per unit for a duration of less than 1 minute. And interruption, either voltage or current is zero for a duration of less than 1 minute. Short duration voltage variations are mainly due to the fault event. For example, if there is a single line to ground fault or double line to ground fault, these faults leads to the, for example, if you take single line to ground fault, at the faulted phase we experience either voltage sag or interruption. At the healthy phase we experience a voltage swell. When it comes to the harmonics, it is also one of the power quality issue which occurs more frequently in the power system due to the connection of nonlinear loads. Nowadays, usage of nonlinear loads are increasing in an exponential manner. Like any, uh, nowadays, all the electrical equipment are equipped with the power electronic components: a refrigerator, a fluorescent lamp, a television, an arc furnace, adjustable speed drives, lift elevators. These are the few examples of nonlinear loads. These nonlinear loads draws a non-sinusoidal current from the supply, and in turn it generates current harmonics. The current harmonics again enters into the source by multiplying its source impedance. It leads to voltage harmonics too. So harmonics are very dangerous in the power system as it leads to many losses in the power system. So harmonics are the main consideration to mitigate in the power supply. Similarly, we have the flicker, one of the power quality issue. Flicker is mainly due to the usage of fluorescent lamps, conventional fluorescent lamps, so that also termed as light flicker. And notches also a very important power quality issue. Because of notching, we can find various different amplitudes in a single or multiple cycles. And voltage unbalanced. So our ideal power system is expected to be balanced in nature, but sometimes the three phases R, Y, B may get unbalanced in terms of phasor and also in terms of their amplitudes. So because of voltage unbalance, the flow of neutral current increases. Due to that, neutral conductor gets heated up. And another power quality issue is the lowering the true power factor. Due to the exponential use of lagging loads and also nonlinear loads, the power factor becomes less than 1. If the power factor is less than 1, it leads to many losses in the power system. See, these are the diagrammatic representation of various power quality issues. So the first one, this one is the indication of bidirectional transient. As mentioned, bidirectional it follows both positive half cycle as well as negative half cycle, and this is the indication of unidirectional transient, where the transient occurs either in positive direction or negative direction. This is the positive unidirectional transient, and this is negative unidirectional transient. And this is the indication of voltage sag, which the amplitude reduced less than 1 per unit for a duration of less than 1 minute. And this is the waveform showing the voltage sag. And this is the indication of voltage swell, where the amplitude is more than 1 per unit for a duration less than 1 minute. And this is the circuit diagram of nonlinear load. Because of connecting nonlinear load, it draws a non-sinusoidal current. Non-sinusoidal current means it is a totally non-sinusoidal waveform and distorted in nature. Due to this, for example, this is the distorted current waveform. In this distorted current waveform, we have the current harmonics along with the fundamental frequency. As you can see here, if you split this distorted waveform using Fourier series, you can find out many harmonic components along with the fundamental frequency. So we have the fundamental frequency 60 hertz or 50 hertz. Along with that, we have the third harmonic, fifth harmonic, seventh harmonic, ninth harmonic, 11th harmonic, and so on. This is the diagrammatic indication of notching, where we get different amplitudes of waveform periodically. That is called voltage notching. And this is the diagrammatic indication of voltage flicker, which is generated by the arc furnace. This is also diagrammatic indication of the voltage flicker, uh, the voltage flicker, which is due to the arc furnace. And this is the diagrammatic representation of unbalanced system, where we can see there is a phasor unbalance is happening. So ideally the phase angle between two phases must be 120 degrees. Here is a phase angle unbalanced system. So because of this unbalanced system, there is a flow of neutral current to the ground. The neutral conductor gets heated up. That is the drawback of unbalanced system. And the lowering power factor. For an ideal power system, the power factor must be 1. If the power factor is 1, the voltage and current is in phase with each other. In phase means the angle between voltage and current is 0 degrees. If it is an inductive circuit, the current lags behind the voltage. This is the phase angle difference between voltage and current. If it is capacitive circuit, the current leads the voltage by 90 degrees. Now, as mentioned, harmonics are the more frequent phenomena in the power system due to the exponential use of nonlinear loads. So, these are the various nonlinear loads which generate harmonics. Bridge rectifiers, both controlled and uncontrolled, arc furnace, fluorescent lamps, lift vehicles, adjustable speed drives, personal computers, and LEDs. These are the various nonlinear loads we use day-to-day life. Because of this usage of nonlinear loads, we can experience a lot of harmonics which generate in the power system. The harmonics leads to many issues. These are the various harmonic effects due to the usage of nonlinear loads. One is increased copper and iron losses. So copper and iron losses are the function of current. So current having the harmonics, so it leads to copper and iron losses. Overheating of neutral conductor, damaging of sensitive equipment, malfunctioning of circuit breakers will happen due to the harmonic effects. KVA burden on electrical equipment, transformer saturation, excessive reactive power absorption, and lowering of efficiency.
Sorry, sir. I think there is some technical problem. Just wait for 2 minutes, sir.
Sorry for interruption, sir. Sir is facing some technical problem. So he will come back within 1 minute, sir, 1 or 2 minutes. Kumaridi, sir. Sorry for inconvenience, sir. Uh, so I think there is some problem with Kumar sir's system. He is not able to connect. The time is also over, so I think we need to stop this session. Sorry, sir. So next session will be on Monday, sir. As tomorrow and after tomorrow we are having international conference in our college. So next faculty lecture series will be on Monday. Okay. Thank you, sir. Thanks for attending.